What's your name? Yeah, just sit one of these people. Okay, so let me just make sure I didn't. Oh, what's your name? Oh, okay. Yeah, so just sit at one of the tables. Okay, so let me just make sure I didn't miss it. I think there's just maybe one person I don't have checked out. Is there a, okay, I think it's pronounced Johani. Johany. Last name is Ceja. What's that? So you know her? Okay, you think she's dropped? Well, if she does drop, there'll be an opening for somebody on the wait list. Okay, but I think that's the only other person. I think I got everybody marked off. All right. The water. This is my third section today, so I need some water. This is CPE133. My name is Gary Perks. I have my first name underlined because that's what I go by. I prefer to be called Gary. And I know for some people, some students, they feel funny about, calling the instructor by their first name. So if calling me Gary makes you feel weird, Mr. Perks or Professor Perks, that's fine. However, don't call me Dr. Perks. I do not have a PhD. I do have 3 master's degrees, one of which is in BECP, so that's what qualifies in the physics class. And, in all honesty, I don't really mind if you call me doctor, even though I don't deserve it. But the reason why I say don't call me Dr. Perks is because in the past, a student has called me Dr. Perks in front of somebody that does have a PhD, that knows that I don't have a PhD, and that person got upset because I did not correct the student. So just to avoid that awkward situation, Gary works just fine. I also respond to hey you, as long as it's in my general direction. So any of those will work, okay? So in today's class, this is what our agenda is. I'm going to lecture on number bases and number base conversion, okay, concentrating on bases that are important for the digital world. Okay, since this is an intro to digital class, we're concentrating on what's important for digital. And then I'm going to have an in-class activity for you. And when you work on these in-class activities, you'll be working with the people at your table. Okay, so it looks like we got mostly 4 people at each table. Now, people looking to add when we get to the activity, and by the way, if you're looking to add, you're more than welcome to stay. Also, if you don't want to stay, that's fine. If you do stay, I'll have you also do the activity. Like I might have you come up to this table, or you can stay at the benches in the back. In fact, I think we have 6 people, so we'd probably go like with 2 3-person groups for the activity. Okay, then after that activity, they'll, during the activity and a little afterwards, there'll be time to take a break if you want to. And then I'll just do kind of an overview of what's on Canvas. Hopefully you've already taken a look at it. And then, start into the lab introduction. And by the end of today's class, you'll be able to do the first part of Lab 0. You won't be able to complete Lab 0 until after Thursday's lecture. Okay, and then Lab 0 is not due until Monday of next week, I believe it is. Okay? All right, so let's talk about number bases and base conversion. So who can tell me what I just wrote on the board? Yeah, just numbers, right? But how many people automatically got 123? Yeah, a few honest people there. Yeah, most people when they see 1, 2, 3 like that, automatically they think 123 because from an early age, we've all been programmed to be base 10, right? Base 10 creatures, right? Because a long time ago, way back, you probably don't even remember when you were first learning numbers, right? You were told that even if it's not explicitly shown, there's this dot right here. What do we call that dot? Decimal point. And to the left of the decimal point, that's how many ones you have, right? And the next one over is how many tens you have. And the next one over is how many hundreds you have, right? And so on, right? Right? You learned that long ago. You don't have to think about it. And then maybe a little later on, I don't know exactly when. Do you remember when you first learned about powers? It's probably like 4th grade or something. It's not when you're first learning numbers. They usually say that till later, right? But you know, sometime later, you learn that this is the 10 to the 0, right? Because any base to the 0 power is 1. And this is 10 to the 1, right? This is 10 to the 2. Then over on this side of the decimal point, you have 10 to the -1, which is how many tens, right? 10 to the -2, which is how many hundreds, and so on. It's all coming back, right? You're like, oh yeah, I remember one time that was 6 plus, right? How many characters do you have in base 10? Like how many digits? Yeah, 10. Right? The number of characters in base 10 is 10. Right? 0 through 9. Right? 0 is a character. See, this that you learned way back when, right? Number of characters is 10 in base 10, and also what these different columns are worth, applies to every base. No matter what base you have, the number of characters equals the base. Also, no matter what base you have, this is going to be the ones column. This is going to be the base to the 1 column. This is going to be the base to the 2 column. This is going to be the base to the minus column. This is going to be the base to the -2 column. Okay. You know, a popular base in the digital world is base 2. Okay, which is called binary. How many characters do we have in base 2? 2, right? Because again, for any base, the number of characters is equal to the base. Does anyone know what those 2 characters are? 0 and 1. Right, 0 and 1. Because in every base, you need a character to describe that you don't have anything. Because in every base, you could have 0, right? You could have nothing. So in base 2, I could have a binary number like this. I could have say 1 0 1 1 0 1 1 0.01, something like that. Now, what you'll typically see, just to explicitly indicate that this is a base 2 number, right? Because this could be a number in a different base, right? Because other bases have 0 and 1. Well, what we'll do to explicitly show that this is a base 2 number is we'll put a subscript 2, right? And that tells us that, yeah, that's binary. Okay. So this column here is the ones column. This column here is the twos column. Like this, see, this column is the ones column because 2 to the 0 is 1. Okay. Any base to the 0th power is 1. This is the twos column because 2 to the 1 is 2. This is the fours column, right? The 2 to the 2 column. This is the eights column, 2 to the 3. This is the 16s column, 2 to the 4. This is the 32s column, 2 to the 5, and this is the 64s column, 2 to the 6. So, you know, just like in base 10, as you go from column to column, right? As you go from digit to digit, there's a factor of 10. In binary, as you go from column to column or bit to bit, okay, because we call 0 and 1. In binary, you call these bits. Right? So just like as you go from digit to digit in base 10, there's a factor of 10. As you go from bit to bit in base 2, there's a factor of 2. Right? And you see this bit here would be the halves bit, right, with 2 to the minus 1, and this bit here would be the quarters bit, 2 to the minus 2. Okay, does that make sense? Any questions on that? Okay, now another base that's not as popular as base 2, but still it comes up sometimes in digital, is octal, which is base 8. So how many characters in octal base 8? 8. And what are those characters? 0 through 7. 0 through 7. Do we have any Jeopardy fans out there? Does anyone watch Jeopardy? You know the game show Jeopardy? Anyone else watch Jeopardy? Jeopardy doesn't seem to be as another person. Doesn't seem to be as popular as it once was. Because in my earlier sections today, it was the same sort of thing. There was only a couple of people that admitted to watching Jeopardy. They were almost ashamed in a way to say they watched it, which I don't understand because smart people watch Jeopardy, right? You win a lot of money on Jeopardy, right? You're smart, know a lot of trivia. But if you ever watch Jeopardy, sometimes they have a category, stupid answers to stupid questions, where the answer is in the question. So you see, this could be a question on Jeopardy under that category, right? How many characters in base 8? 8, right? The answer is right there in the question. So you could have an octal number like this. You could have, say, 2, 7, 3. Now, I didn't mention this earlier, but I did mention earlier that this is called a decimal point. In any other base other than base 10, this dot is called a radix point. Right, because decimal means base 10, right? So you see, it wouldn't make sense to call this a decimal point in any other base other than base 10, because again, decimal means base 10. So in any other base, we call it radix point. Radix is just another word for base. Okay, radix and base mean the same thing. So getting back to this, I could have an octal number like 273, radix point, 0, 5, let's say. And what would this column be worth? What would it be worth? This column just to the left of the radix point. 1, right? That's your 1's column, right? Because that's 8 to the 0. Okay, and then what would this column be worth? 8's. Right, because that's the 8 to the 1. And then what would this column be worth? 64. Because that would be the 8 to the 2 column. Okay, and then how about over here? What's this column worth? 8 to the minus 1, which is 8, right? And then what's this column worth? 64. 64, right? It would be 8 to the minus 2, so 64. Okay. Right? So do you see how what you learned a long time ago with base 10, it applies to any base, right? Number of characters equals the base, and then what the columns are worth. It's the same concept as what you learned about base 10. Now, like I said, octal is not as popular in the digital world as binary is. I mean, binary is very popular in the digital world. And another base that's as popular as base 2 in the digital world is hexadecimal, which is base 16. Okay, a lot of times we'll just say hex. Okay, hear someone say hex. They talk about digital stuff. They're referring to hexadecimal. Okay, so hexadecimal base 16. How many characters? 16. Does anyone know what characters we use?
0 through F.
Right. Yeah, the first 10 are 0 through 9. And then we start using letters. Okay, so A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. And I wrote all the letters as uppercase. And in my experience, most of the time, in a hexadecimal number, most of the time, capital case is used, uppercase is used. However, that's not something that's standard. I mean, sometimes you'll see the letters as lowercase. In fact, you'll see in a lab in this class later on in the quarter that because of a limitation of a display, for certain letter characters, we have to use lowercase. Okay, and you'll see the reason why when we get there. It's not for a few weeks. But even in the follow-on class of this class, CPE133, you know, you're likely to see lowercase letters and hexadecimal when you take that class. So, like I said, even though in my experience, mostly you'll see the uppercase for hexadecimal when you get to the letters, don't be surprised if you see lowercase. Okay, it's not something that's like standard. But you could have a number like this in hexadecimal. You could have A8, F3, radix point, C. And you could have something like that. So what would this column be worth? What would it be? Right? This is always the ones column because it's the base to the 0th power. What would this column be worth? 16. What would this column be worth?
16 squared.
16 squared. Does anyone know what 16 squared is?
256.
256. Yep, 256. And then what's this column? 16 cubed. Does anyone know 16 cubed? 256 times 16?
4096.
Yeah, very good. 4096. Okay, and then how about this column? What would it be worth? 16 to the minus 1, which is 16th, right? I mean 16. Okay. So, any questions up to this point? If there's no questions up to this point, the next thing to do is to see how to convert between some of these spaces. Do you have a question?
So it doesn't matter if it's lowercase, like all the letters, it doesn't make a difference.
No, I mean, like I said, most of the time I think you'll see it as uppercase, but yeah, you could see this as, you know, like. And it's the same answer, it's the same, yeah, the case doesn't change anything. Any other questions? All right, so let's do some base conversion now. And I'm going to show you the most common conversions that you need to do in this class and also in CPE133. Okay, the following. Okay, this class is a very important prereq to CPE133. So throughout the quarter, you're going to hear me saying that a lot. And CPE133, you really need to know this. And these conversions is something you really need to know. So let's start with, I don't want to go out of order here. Let's start with going from base 2 to base 10. Okay, so somebody give me a base 2 number. Just give me a string of 1s and 0s. What do you want first?
0, 1, 0.
0, 1, 0. Yeah. Let's do some more. Let's have maybe like 8 bits or so. What do you want after 0, 1, 0? 1, 1, 0, 1, 0, and let's put a radix point. Then what do you want to the right of the radix point? You can do a couple. 0, 1. Okay, that's good. Okay, well, to take this base 2 number and convert it to base 10, just look at what each bit is worth, right? What each column is. So this is the 1s bit, 2's bit, 4's bit, 8's bit, 16's bit, 32's bit, 64's bit, 128's bit. This is the half bit, and this is the quarter bit. Everybody sees what I'm doing, right? I'm just going 2 to the 0, 2 to the 1, 2 to the 2, right? 2 to the minus 1, 2 to the minus 2. Right? So now, wherever there's a 1, it means you have that value. Wherever there's a 0, you don't have that value. So you see, we don't have a 128. We do have a 64. We don't have a 32. We do have a 16. We do have an 8. We don't have a 4. We do have a 2. We don't have a 1. We don't have a half. We do have a quarter. And then you just add these up. Okay, now, please, if I make an error at any time, you know, this class, next class, any class this quarter, if you catch me making an error, please point it out. Okay, don't be shy. Don't let me keep going if I make a mistake. I do not try to make mistakes on purpose. You know, some instructors will do that to see if you're paying attention. I don't do that. When I make a mistake, it's a legitimate mistake. I made a mistake. And so always check what I'm doing. All right, so if we add these up, let's see, this will give us 80, right? Then 88, 90. So I get 90 and a quarter. So 90.25. That's what our base 10 number would be for these bits for this base 2 number. Okay, does everybody agree with that? Okay. Does anyone want me to do another example, or is this, you get the idea? Right, but yeah, it's a different string of bits, it's still the same approach. Right, you're just adding up where the ones are. Okay, so everybody good? You don't want another one? All right, let's go from base 10 to base 2. Okay, so give me a base 10 number. You don't have to give me something crazy, you know, maybe something in the thousands. Somewhere, you know, a couple thousand, several thousand. You know, it doesn't have to be like a million or a billion or something like that. You'll get carried away. Give me a number. Base 10 number.
1, 2, 3, 4, 5.
1, 2, 3, 4, 5. Is that what you said? Okay. So 12,345. Now, I'm going to show you the way that I like to convert base 10 to base 2. There are other ways to do it. In fact, you know, I've learned through past experience that some students that take this class have already had some of this material at their high school. And often in high school, there's this particular algorithm that's taught. Okay, so if you know what that algorithm is that you learned earlier and you like that way better than what I'm going to show you, that's fine. Okay. But you see, what I would do to convert this base 10 number to binary is, again, I'm using that whole columns approach, right? What each bit is worth. So I would start off with, you know, 2 to the 0, that's how many 1s, then 2 to the 1, how many 2s, then 4s, then 8s. Right? I would just keep on going. Right? Remember, as you're going from bit to bit, column to column, it's a factor of 2. Right? So here would be 128s. Then this would be 256s, and then 512s, and then 1,024s, and then 2,048s, and then what this would be 4,096s, and then this would be, let's see, 8192s, I think. Yeah, right, 96 times 2 is 192. And then this would be 16,000 something, but see, I don't really care what this one is because I already know that 16,000 won't go into 12,000, right? So you see, I know this bit is going to be a 0. Well, we can put it. Let's see, 192 times 2 would be, let's see, that'd be 3, is that 384? You double this, is that right? Because 192 times 2 would be 16 less than 400, right? Everybody agree with that? Okay, but regardless, like I said earlier, you know, whatever this is, 16,000, whatever, it's more than 12,000, so we know that's gonna be zero, right? There's no 16,000 to 12,000. Okay, but we do have an 8,192 and 12,000, so you see, that would be a 1. And then I would subtract that from my 12,000. Right, so let's see, this will give us 4,000. Would be 153, would it be? Yeah, if I make a mistake, let me know. I think that's right. 4,153. All right. Now I look at this number and I look at the next column. Well, there is a 4,096 in 4153, so that would be a 1. And then I subtract that from this. That'd be what, 157? That's right. Okay, well, there's no 2,048s in 157, so that would be a 0. There's no 1,024s in 157, so that would be a 0. There's no 512s, that would be a 0. There's no 256s, that would be a 0. But there is a 128 in 157, so that would be a 1. So subtract 128. That would give us what, 29? Okay. There's no 64 in 29, there's no 32 in 29, but there is a 16. So we subtract 16. Okay, and there's an 8 in 13. There's a 4 in 5. And then I'm left with a 1. Right, no 2, but there's a 1. Okay, so you see, 12,345 in base 10 would be, now you don't have to say this 0. Right, any mean 0, it doesn't matter. So you just start here, it's 1, 1, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, binary. Okay, so everybody see what I did there? You know, the algorithm that some people learn in high school is that if you take the same number and you successfully divide by 2, and if there's a remainder of 1, then the bit is 1. If there's no remainder, the bit is 0. You know, that's another way to do it. I don't really like that way because it's kind of just rote. You know, this is showing more reasoning, I think. That's why I like it. But like I said, if you know a different way and you're more comfortable with that other way of going from base 10 to base 2, then that's fine. You can use it. Okay. So, any questions on anything up to this point? Everybody's good? You have a question?
Subtract 1496 from 4153.
Did I make a mistake?
I don't think it's incumbent.
This right here? Well, this is 4 from being, oh. You're right, isn't it just 57?
Yeah.
All right, well, now we gotta go back and readjust here. Oh, well, let's do this. It was 100 off, right? So let's say this was this. Okay, now it's right. Okay, but thank you, but if at all possible, let me know before I go too far. Because I'm likely to, but thank you for telling me. Like I said, I make mistakes, so you gotta watch out. All right. Any other questions or anything else at this point? Okay, let's see, base 16 to base. All right, so base 16. Base 10. Okay, so somebody give me a base 16, you know, let's say 4 characters, and you can do like 1 character to the right of the Reagan screen. So give me the first 4 characters, somebody, and mix it up with letters and numbers. Don't have all the numbers or all the letters. What do you want as the first character? Very indecisive group. There is no right or wrong answer, you know. Whatever you say, well, I take that back. There could be a wrong answer. What would be a wrong answer? If I asked you for a base 16 number, what could you give me that would be wrong?
The letter after that.
Yeah, like if you gave me like G something, right? Because there's no G in in hexadecimal, right? You can only put the letter up, so that would be a wrong answer. But anything other than that, it's gonna be correct. So what do you want as the first character? A, thank you, A. How about the second one? 2. 9, okay, now a letter. B, okay, and then radix point, what do you want to the right of the radix point? Okay, good, thank you. Okay, so the way that I would convert this to base 10, again, is just looking at what each of the characters, each column is worth. So this would be the ones, right? 16 to the 0, this would be the 16, 16 to the 1, this would be the 256s, 16 squared, this would be the 4096s, right? 16 cubed. This would be the 16, right? 16 to the minus 1. So now, what is A? What number is A in hexadecimal? 10. So we have 10 4096s. And we have 2 256s. And we have 9 16s. And what number is B in hexadecimal? What is it? 11. So we have 11 ones. And then what's F? What number? 15. We have 15 16s. So now you just gotta multiply out and add. So this is gonna be, yeah, thanks for making this A, whoever said A, because that makes this easy, right? This is just 4,000 or 40,960. Multiply that by 10. Then this is by 12. Let's see, 9 times 16, that's gonna be, what is that? What is it? 150? 154 or 144? It'd be 90 plus 54, right? 144? Okay, thank you. Yeah, simple math always looks more difficult when you're up in front of a whiteboard. You know that, right? Sometimes when I'm up here, I think I would forget my name if you ask me. Too much pressure. Okay, so this would be 11, that's an easy one, right? And then this would be 15 over 60. 15 over 60. All right, now you just gotta add these up. Right, so this is gonna give us, if we add these two, we'll get what, 41,000. What is it, 472? Yeah, 41,472. Then we add 144 to that, that's gonna be 41,000. Let's see, 616, is it? 616, I think that's right. Again, if I make a mistake, but, oh, wait. No, I think that's right. Is that right? Is that right?
I think so.
When you add 144 to this, because if you add 150, it's 60, because it subtracts 6. I think that's right.
No, it's not here.
Yeah, all right, thank you. And then 41,627. So the answer would be 41,627 and 1560. Okay. So any questions on that one? All right, now let's go from base 10 to base 10. There's no questions, I can erase this. Okay, so base 10. Base 16. So give me a base 10 number. Again, not something too crazy, maybe something in the tens of thousands somewhere. What number do you want? Okay, say it again. I'm sorry. 1,023? Let's make it 10,000. 10,233, you said? 230. Okay, so same approach. You write out what each character, each column is worth in base 16. So again, we're gonna have the ones column 16 to the 0, then the 16 column, right? 16 to the 1, then 256, 16 squared, then 4,000, 96, 16 cubed. Okay, what is 16 to the fourth power? Calculate. Yep. So 16 to the fourth power is 65,000. Say it again,
536.
536. All right, so see, when I write out these columns, I always go one more than what the number is, right? Because then I know that's 0, and then the next column is gonna have some value, right? Because there's no 65,536 equals 10,233, so this would be a 0. Okay, but how many 4,096s are in 10,233? How many? 2, right? Okay, 2 times 4,096 is gonna be what? It's gonna be 8,000 192, right? You get that? Right, because you double 4,000, 8,000, double 96, that's 8 less than 200, right? Okay, so now you subtract this from here, so it's gonna be 2,000 141. Everybody agree with that? Okay, so now how many 256s in 2001? Whoop, did I make a mistake?
That's 2041.
This is wrong.
That's 2041.
Ah, I did it again. I like adding a 100, don't I? You don't want me doing your taxes, right? I'll get you in trouble. All right, thank you. Yeah, it's 2041. All right, so how many 256s in 2041? That'd be less than 10, right? Because 10 would be 2,570. How many? 7? Did you do 7 times 256? What is it? What's this? Did you do this?
I did 2041 divided by.
Oh, okay. Can you do 256 times 7? What is that gonna be? It's gonna be 2 carry the 4, 9. Is it 1792? That doesn't seem right. Is that right? Oh, it is right? Okay, so 1792. Yeah, I thought this might be over 256, but it looks like it's less than 256. Is it like 249? When we subtract 2041, or when we subtract 1792 from 2041, do we get 149? Or 249? 240. Yeah, that's why I thought this wasn't right. It seemed like it was on 256. But it's less than 256, so that's okay. All right, so now how many 16s in 256? It's probably close to 15. Well, how many 16s in 249? 15. Was it 15? Yeah. Oh, okay. And what's 15 in X? Yeah. Let's see. 16 times 15. Gonna be what? 160 plus 80, right? 240. Is that what you got? 240? Yeah. All right, so minus 240, so we're left with 9. So this would be a 9. Right, so that's your hexadecimal for 10,233. It's 27F9. Okay. All right, so everyone's confident that you can go base 2 to base 10, base 10 to base 2, base 16 to base 10, base 10 to base 16. Okay, because now what I'm going to show you is how you can go from base 16 to base 2 or base 2 to base 16 directly without going through base 10. All right. And what I'm about to show you is very important for this class and also CPE133. It will save you time. So I'm gonna show you how to go first from base 2 to base 16 without doing base 10. Right, because you could go base 2 to base 10 and then go from base 10 to base 16. Right? 'Cause, I mean, that's what we were doing with the earlier example. Okay, but there's a way that you can go directly from base 2 to base 16. And this method of going directly between these two bases is based on that 2 to the 4th power is 16. Right, 2 times 2 times 2 times 2 is 16. So what I can do is, let's say we have a binary number like this. Let's say we have the following. Say we have something like this. So that's our base 2 number. Well, what we can do to go directly from this binary into hexadecimal is starting with the least significant bit. So the bit that's furthest to the right, so this bit here, it's called the least significant bit. Okay, or LSB for short. And then the bit that's furthest to the left, this is the most significant bit. Okay. So starting with the least significant bit, group in 4-bit binaries. You see, I'm going to make this a 4-bit group. 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 And then if you have a situation like this where you have a number of bits left over that's, it's not 4 bits, well, you can just add zeros right to the front of it, because when I add zeros to the front of a number, whether it's base 2 or base 10 or any base, I'm not changing the value. Okay? And you see the reason why we're doing groups of 4 is because of this 4th power. The relationship between 16 and 2 has this 4th power. Okay, so now I write the hexadecimal character for each 4-bit group. So, we're looking at these 4 bits here, and this is the 1s bit, this is the 2s, this is the 4s, this is the 8s. So what is the hexadecimal character for 0101? 5. Right? So this is 5. Right, I got a 4 and I got a 1, and 5 is a character. Okay, then you do the same thing for the next 4 bits. This is the 1s, 2s, 4s, 8s. So what's the hexadecimal character for 1100? C, because it's 12 and hex. C is 12. Okay, then we do the same thing for this 4-bit group. 1101. What would that be in hex? What would it be? D. D, right? Because 1101, that's 13, and in hex, 13 is D. Okay, and you do the same thing for this 4-bit group. So what would I put next? 0011 is what in hex? 3. Right, we got a 2 and a 1, and then this would be a 1. So 1 0 0 1 1 1 1 0 1 1 1 0 0 0 1 0 1 in binary is equal to 1 3 D C5 in hex. And if you don't believe me, if you don't believe that this works, on your own, take this number, convert it to base 10. Take this number, convert it to base 10, and you're going to see it's the same number. Guaranteed. Oh, you mean when you're grouping?
Yeah.
Well, that's what we had originally. Cause I just had this single bit here, but you would just add zeros.
Oh, yeah, because they did something to do.
Right, exactly. Yeah. Yeah. Okay? Now, this also works the other way. Like, this was going from binary to hex, but you can use the same approach going the other way. Like, say I had this base 16 number. I had, let's say, A3, B4. We'll just leave it there. Well, I can write each hexadecimal character as a 4-bit binary group. So I can write this 4 as a 4-bit binary. That would be 0, 1, 0, 0. And then C in 4-bit binary would be 1, 1, 0, 0. And then 3 would be 0, 0, 1, 1. And then A, which is 10, would be 1, 0, 1, 0. Okay, so you see A3, C4 in hex is 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0 in base 2. Okay. We said earlier that octal is base 8. What power of 2 equals 8? 3. So if we had a binary number that we wanted to convert to octal without going through base 10, we would take the binary number and make groups of 3. Again, starting with the least significant bit, and then write each 3-bit group as an octal character. Right? And that will convert directly from binary to octal. And again, you can go the other way too. If you write each octal character as a 3-bit binary group, then you can go directly from octal to binary without going through base 10. Okay. In CPE133, you build a microprocessor. Okay, you take what you learned from this class and you kind of take it on steroids, if you will. And you make this microprocessor that's probably like an order of level of difficulty more than the most difficult design you do in this class. Okay, so 233, like this class, is a challenging class. But anyway, that microprocessor that you build in CPE133, it's a 32-bit microprocessor. And what's meant by a 32-bit microprocessor is that the data that microprocessor processes is 32 bits. So if you have something that's 32 bits, how many hexadecimal, what's the minimum number of hexadecimal characters that can represent 32 bits? 8. How'd you get it? Yeah, you just take the 32 bits and divide by 4, right? Because as you see in this technique, every 4 bits is 1 hexadecimal character, right? So if I had 32 bits and I group in 4s, that's going to give me 8 hexadecimal characters. And you see, the reason I mention this is because a reason why hexadecimal is so popular in the digital world is because a lot of times, in actual practical digital circuitry like microprocessors, often you have a lot of bits that represent something, data, whatever it may be. Well, it's much easier to say 8 hex characters as opposed to 32 bits. Instead of saying 0, 1, 1, 1, 0, 0, 32, I can just say 8 hex characters and it means the same thing. So base 16 is sort of like a shorthand for binary, right? Because in 1 hex character, I'm actually saying 4 bits. Back in the day, before you were born, most of you, not all of you in this class, computers, when you would boot up computers, you would actually see the computer going through the tests before it would give you control. Like, you don't see it anymore because it's hidden. I mean, there's ways that you can see it if you want to. If you're like a computer hack, there's a way that you can go in and actually, I forget the menu, but there's a menu that you can actually change the settings and see it happening. But back in the day, all computers were such that when they booted up, you would actually see it going through the test, like it testing out memory and testing the peripheries before you would actually get to the desktop. And when it was going through those tests, what you would see on your screen is just a bunch of hexadecimal numbers. You'd have like F, DC, whatever, and da, and it just keeps scrolling. And what you were seeing, where you were seeing all the bits of the different data, you were just seeing it in hexadecimal. Okay, so where are we at here? So that's what I wanted to talk about before the activity. So let me go ahead and give you some general information about the activity, then I'll give you the activity itself. It's on Canvas. And again, the activity you work on at each of the tables, it's a group type of activity. You can also take a break at some point as you're doing the activity. But like I said, let me give you some general information here. In fact, let me get my phone out because I want to give you the same information I gave my other classes. Make sure you all get the same thing. I took a picture of what I told the other classes, so I don't want that. That's the camera. Where's my? Yeah, here we go. Okay, so in-class activity. Okay, first thing is to get credit for an in-class activity, you have to be physically present. Okay, so there's no like makeups for in-class activities because they're in class. So if you miss a class and it's for a university recognized reason that's documented, I just won't count that activity. But if you miss a class and it's not for a university recognized reason or it's not documented, then it's just scored as 0. And in the syllabus, I give examples, the most common examples of university recognized excuses, like being sick. You got some other school activity, like you're an athlete or you're in the band or something. And if it's a university recognized excuse and it's documented, so for example, if you're sick, I do have to have like either a note, a doctor's note or something from the health center or something that shows you had an appointment at the health center. I mean, that works. Or if it's something school related, like if you're an athlete or you're in the band or some other club or something, usually they'll have letters that, like for athletes, the athletic director will send a letter out saying, please excuse this student if they're doing whatever they're doing for the school. So anyway, if you can't be here, and again, if it's for a university recognized reason and it's documented, it just won't count. Okay. And if you go to the Cal Poly website, they have a whole list of, what's considered a university recognized reason for, doing that. Okay, so that's the first thing. You have to be here to get credit for the physical activity. Each student does their own work. Okay, and you have to show your work. Okay, I provide answers to the activities. So as you go through the activity, you can check to see if your answer matches mine. But I need to show, or you need to show me that you actually did work to get that answer. Otherwise, I don't know if you just wrote down my answer. Okay. So make sure to show your work. And also this gets you in the habit of showing work for your problems, because on a midterm, I don't grade on answers. I grade on the work shown. So on a midterm, there's been cases, this doesn't happen a lot, but it has happened where a person will have an answer that matches mine, but they show absolutely no work. Like, I don't know where that answer came from. And in a case like that, it's 0 points, right? Because again, the answer doesn't mean anything to me. It's the work that shows me your understanding. And that's what I'm grading on, your understanding, okay? What happens more often than not on a midterm is somebody will have an answer that's different than mine. And in some cases, like a lot different. But I look at their work, and the only reason their answer doesn't match mine is because somewhere in their work, they made a silly mistake. Like they added 2 + 3 and got 7, something silly like that, which I just attribute to stress on the test. So, in a case like that, the person's going to get full credit or nearly full credit. I mean, probably at least 95%, if not full credit. Okay. So again, what's important to me is showing that you understand where your answer came from, not just having an answer. Okay, I got to see how you got it. Okay, so make sure to show your work. And then it's just, you're going to be working on these in-class activities in groups. So, this is going to be group number 4, right? Table 4, group number 3, group number 1's over there, group 8, 7, 6, and 5. Now, the 4 people in the back looking to add. When we start the activity, you can come up to this table and you'll be grouped through. And just when you turn it in, just make sure to write that you're looking to add, so I know you're the people on the wait list. Okay. And you just make 1 submission per table. So 1 submission per table. So you're all doing your own thing, but then just turn in 1 for your table. People that, make sure everybody's name is on there. Also put the table number on there. And you can either hand in, a copy where you handwrote your work and answers and so on. Or we do have a printer. So, if you do it on a tablet or something and you want to print it out, that's fine too. Okay, I let the groups at the table decide, what to turn in. Like some groups, they just say, oh, you turn in yours this time, like one person turns in theirs for the group. Other people, sometimes what they'll do is they'll turn in more than 1 and they'll say, okay, these 4, from this person and these 4 from this other person. However you want to do it, that's fine. But you want to make sure everyone's doing their own work. What I don't want to see is okay, you do these 2, I'll do these 2, splitting it up. Everybody does all the problems because, if you go to split it up like that, well, when it comes around to midterm time, you're not going to be able to split it up then, right? So you have to make sure, each person's going to make sure that they can do all the problems. It doesn't work with splitting up like you do with lab reports. Most of the time, I think, is in my experience. Okay, let's see. Anything else? So yeah, physically present. Each student does their own work. Show your work. And also, since I'm giving the answers, right? You have the answers. When I grade these, I grade on completeness. Completeness. What's that spell? I don't know if there's an E there or not. Since I'm giving you the answers, it doesn't really make sense to grade on accuracy, right? Because you got the answer. So I just grade to make sure you turned in everything, you did all the problems. I don't look at, what you got because, I'm leaving that up to you. You should get what I got. Okay. Now, again, on midterms, I grade for accuracy. Okay, but for these activities, it's graded on completeness. Okay. All right. So the first activity, I got to turn on this projector. Okay, it's on Canvas. Let's turn this on. It's warming up. So on Canvas, where this is located, under modules, if you click on Meeting1a, you right here, it should be more. You can download it. Yeah, download it. But it's these 11 problems. It's all to do with bases and base conversion, and, there's another page of this Word file that has the answer right below it. Okay? But like I said, at some point during the activity, you want to take a break, that's fine. Hopefully, by the top of the hour, most people will be either finished or near finished, so, right around that time, I'll check to see how many people are done. If you need a little bit more time, I can go a little bit more. But I do want to cover, go a little bit over what's on Canvas and also, introduce you to the Lab Zero before you leave today. Okay? So go ahead and start working on the activity. Again, during the activity, if you get stuck, there's no reason to remain stuck because you can help each other and you can ask me questions during the activity. Okay?